Okay, now here on your right hand side, concrete poles, 33 kV lines, a suspension pole with pin insulators, and right at the bottom on right hand side you have a tension point with disc insulated string. So that is how the distribution lines are conducted and constructed. And on the other pictures on extreme right hand, extreme left hand side, you have a monopole line. So we can see a double conductor per phase on the monopole line. Looks like okay, 132 kV line, and the other one also a 132 kV line monopole, and the other one we are very familiar. That is, of course, a lattice tower construction. So lattice tower constructions are there in Sri Lanka, many, and you are familiar with this. And we'll come to the next slide. Insulator types. So these are the disc insulators and also called cap and pin insulators. Cap is right here and pin is here. Cap is here, pin is here. Okay, now this clevis, the pin of the other insulator can go into this clevis and it can be locked with a locking pin. And that is how you make a insulated string. So on the bottom, you can see an insulated string combined with cap and pin insulator construction, a 66 kV line. And on the top, your jumper goes on a pin insulator. Now, here you can see the pin insulators, pin insulator here, and another variety of pin insulator with higher creepage. We'll come to explain what is creepage area, creepage distance, and then this insulator, this is used for 33 kV, this is also used for 33 kV, and this insulator has higher creepage. I think you can see my pointer, no? Sashika?
Yes, sir, we can see.
Yeah, and this is a long rod insulator. On the bottom also, here it's a long rod insulator, porcelain, and combination of porcelain long rod insulators. And these are very commonly available as polymer insulators, long rod polymer insulators, not only porcelain insulators. The long rod polymer insulators are more popular and used. Okay, now we'll see quickly at a disc insulator. This disc insulator has collars. These collars. Now here you have the iron, that is cast iron cap, and this area is bonding cement, and this area is again the insulator. So from this point of metal to again to the point of metal, the distance along the surface on collars is called the creepage distance. Remember, now creepage distance is needed for your selection of the insulator. Now here you get a pin insulator with polygon, okay, several polygons, and in between cement and a pin right over here. It's held up with a pin and connected to the tower or the cross arm with a pin. Now this is a long rod insulator, and you have your sheds. These are the sheds, and the sheet all are with polymer, and in the middle here you have got either fiberglass reinforced plastics or polymer that is called the hard core, polymer core, and with around the polymer core you have the polymer sheds and sheath, and connected to one side is connected to tower, and one side is connected to the conductor, and so on. Okay, now transmission line hardware. This is a suspension clamp. There are so many, hundreds of different types of suspension clamps, and this hung right over here. When the conductor goes through this, and at the suspension point you have some sort of a rigid point, this tends to vibrate over the suspension clamps where you are holding. And because of the vibration, if you have any sharp edges, conductor would cut and get damaged. That is why you have a rounded off tongue over here. And suspension clamp is on a suspension string connected like this. And here also, it's the line conductor goes through the suspension clamp, and the suspension clamp here is connected to a hardware called eyeball. I'll show you eyeball in the next slide. And eyeball is again connected to a clevis so that it can be connected to the tower over here. It can be connected to the pin over here on the insulator. So that's how with the insulator string conductor is held. And this shows, of course, a yoke, and this carrying two conductors and a long rod insulator over here. Yeah, rod insulator, suspension points, rod insulator. Now, this is the eyeball, what I talked about, and this is the other device. This part goes into, this clevis goes into the pin of the last insulator, and this can be connected over here. So this is again a porcelain long rod insulator, and on right hand side insulator cross arm V-shaped, and your suspension clamp can be connected over here. Here also this I-type insulated cross arms, and your suspension clamp can be connected at the end of this insulator. So these are normally called insulated cross arms, long rod insulated. And these are not yet used in any other Sri Lankan transmission lines, but normal insulators like the configuration what we have seen over here is employed for 33 kV horizontal formation double circuit lines. Okay, anyway. So again, this one is a vibration damper connected on conductors. These are called helical components. All these can be used as dead end clamps at the tension points. Now, this one is very popular with OPGW. OPGW cannot be, cut and connected everywhere, cut and bolted everywhere, so that you can have jumpers and whatever. As far as possible, you are continuing that. Even at the jointing point, you continue down to a point and splice the splice the fiber cables with each other on the from each side, and the dead end clamps are clamped with these sort of helical components. This part of course can be wrapped over the conductor, and this part can be anchored to the tower. So now I know that when I'm talking about this and OPGW, you might ask, what is OPGW? That is another conductor, that is earth wire on the top of the transmission line that carries fiber optics in a small tube in between other strands. So that is OPGW. So that OPGW is generally connected with this helical components as the tension points. This also a bolted tension point. This is also a bolted tension point. And in other conductor, there are many hardware components for transmission lines, but I have taken few of those. Now these are spaces when you have lot of conductors. Okay, 4 conductors and 6 conductors. So these are the spaces you are placing when you have 6 conductors per phase. Now, you might have seen 2 conductors per phase in transmission lines in Sri Lanka, but there are 6 or 8 conductors sometimes in a phase on a transmission lines. So next one. So this is the dead end clamp, what we have seen over here, and that dead end clamp conductor is fixed on this one, bolted and tightened, and come out over here. And on the other side of the tower, similarly, the conductor comes over here, and both conductors are at a midpoint connected with a parallel groove clamp. And this one is a crimp type dead end clamp. So conductor is connected here, and first of all, you push this part through the conductor right down, and then you get this part and crimp it to the core of the conductor. So now at this point, I know you have a problem. Okay, what is the core of the conductor? So ACSR conductor, that is aluminum conductor, steel reinforced, has a steel core. That steel core takes the stress, the tension of the conductor. So that core is connected over here, and it's going through this because okay, you can push now to this side, so it comes over here, and in this part the aluminum part is crimped finally. Then for the jumper you get this one, crimp it here, this lug, and connect it, and then you have the jumper. So these are the conductors. Okay, all aluminum conductors doesn't have a core. That is all aluminum. All these strands are aluminum, and okay, these are the conductors used for LV lines, 400 volts lines in Sri Lanka, and very rarely these also are used inside the substations for very slack spans. Whenever substation has bus connections as stranded conductors. Now, this one is with a steel reinforced core. So this is the one, aluminum conductor, steel reinforced. So this is called ACSR. This one is called AAC. And this one is called AAAC. AAAC is aluminum alloy conductor, all aluminum alloy conductor, right? These are the conductor types. And also now there are some other low resistance, low loss, and low sag conductors, out of which now in the world ACCC conductors are becoming very popular. So ACCC conductor is aluminum conductor composite core. So the conductor Amsterdam. Now conductors have names actually. Now British conductors in ACSR conductors, they have put given names, okay, the code names with the animals names, zebra and lynx and dog and raccoon and so on and on. So those are British standard ACSR conductors. If you go to Australian standards, ACR conductors of similar sizes of lynx, zebra, and whatever that is used in Sri Lanka, they call the conductors according to their standards by name of fruits. Okay, cherry, lime, and so on. And ACCC conductors are always called by the names of cities. So ACCC conductor Amsterdam, the conductor's cross section, nominal equivalent aluminum area, and cross-sectional area of aluminium, and cross-sectional area of the core, composite core. So composite core is this one, and that composite core takes the stress of the conductor when that is put on the line. Total area of cross section is given here, and overall diameter and maximum mass per length, mass per unit length, and yeah, and maximum DC resistance, and also maximum AC resistance is given somewhere here. Okay, outer layer aluminum wires and whatever, lay direction, right hand, and number of diameter of the composite core, number and diameter of number and aluminum layers, and so on and on. Conductivity and yeah, coefficient of thermal expansion, modulus of elasticity, and here AC resistance, and so on. Now, this conductor can be operated even at 180 degrees, 175 degrees, and current that can be used is given as, yeah, is increases with higher temperature. So, you know, I squared R, you emitting heat, and conductor gets heated up when the current is high. So with 1300 or 1000, yeah, 350 ampere, the conductor can be operated at 175 degrees. Now, the previous ones, these conductors can be operated up to 80 degrees only. And by using the composite ACCC conductor, you have the advantage of you can operate at higher temperature, and your sag is lower, and your weight is lower. Now, when you are designing a new transmission line, if you comparatively use a low weight conductor, what happens is your structure would be lighter and your foundations would be smaller. So you have those advantages when you are using ACCC conductor. Okay, these are the properties. And part 2, design of transmission lines, line profile design theory, selection of insulators, selection of conductors. So line profile design theory, when I do halfway, I'll hand over to Vinavi, who has already joined. She would explain the PLS-CADD design method and how we do the design with PLS-CADD software. So after that, I am taking over again. And while we are changing over after line profile design theory, once I do halfway, we'll get a small break. So you can have your snack and tea if you want to. and keep on asking questions up to whatever I have done. Then we will start doing the demonstration of PLS-CADD design. Okay, now profile design, second tension. So on that, we are going to derive an equivalent span and selection of tension. Equivalent span. So the equivalent span is calculated in order to use sag tension charts. The tension is uniform between two sections of poles and supports on intermediate poles. Now, what I mean by a section, you have tension points on a line and you have suspension points on a line. So from one tension point to the other tension point, the next tension point is a section. So in between, the tension is same. So this is okay. The first one is one tension point, and the other one is the next tension point, and S1, S2, S3, S4, and on. From one tension point to the other tension point, you get the length of spans, and then equivalent span you can derive by this equation. So S1 to the power 3 and S2 to the power 3 and divided by S1, S2, S3, etc. Square root of that is called equivalent span. So where S1, S2, S3 are individual spans between section poles, that is tension poles, having determined the sags and tensions on the equivalent span at various temperatures, the sags on the actual span can be determined from the formula. This one. The sag on any span, sag on equivalent span, actual span square over equivalent span square. So with this equation, you can get the sag on any span. Next one. Yeah, this is the equation. So having determined sag on any span, the pole spacing can be finalized. The maximum span is within limits of 5% of the span according to the, yeah, this was done for, I have taken this from a design and the presentation that has gone to Vizag, India. And Indian practice for 33 kV lines, maximum 70 meter span, maximum shall be 3.5 meter. So these are from there, this thing, but our standards are different. While fixing spacing, it should be as uniform as possible and maximum ground clearance should be maintained, which is specified as 6 meters on road crossings and 6.4 meters. The clearance on road crossings are 6.4 meters. The clearances are more, leaving room for tap off, etc. The maximum sag for different pole heights can be obtained from sag table. We'll see the sag table later on. Selection of tension. The maximum sag will occur at defined maximum operating temperature 65 degrees. Okay, always now say if we are designing a transmission line with ACCC conductor, so that can go up to 180 degrees. So here, this particular line has been designed for temperature of 65 degrees, and the maximum sag will occur at 65 degrees no wind. So if you are designing a ACCC conductor, then 170 degrees no wind, at that condition you get the maximum sag. The maximum tension will occur at the lowest temperature with wind. The constant tension occurs at defined normal everyday temperature of 27 degrees. Now, everyday temperature is taken in India as 27 degrees, and in Sri Lanka is 32 degrees. What is everyday temperature? Everyday temperature is the ambient temperature that this transmission line we are designing going to face in most of the time of its life. So everyday temperature, the tension is specified normally, and for maximum temperature, the Indian standards 4.9% is specified, but for transmission lines and all, okay, we'll see what are the tensions of transmission lines in Sri Lankan standards. Second tension formula is generally this, and it is approximated to this equation. So on this equation, W is the conductor weight, Newton per meter, and S is the sag, T naught is the tension at lowest point, and L is the horizontal distance between two supports, and T is the conductor tension. So yeah, so this is the equation. After a conductor has been fixed into position, variations in the consequent consequently due to wind pressure and temperature variations can be calculated from this equation. So this is a third order equation, right? T23 to do the T2 to power 3, right? So this equation can be, sorry. This equation can be, yeah, derived with Newton-Raphson method, and here T1 is T0 in initial conditions, T2 is T0 in final conditions, X is coefficient of thermal expansion, A conductor area, E Young's modulus, theta 1 is conductor temperature, final conductor temperature theta 2, F1 is the resultant wind and weight forces, and F2 is a resultant weight force in final condition. So that is the equation. So conductor tension in Sri Lankan standards, at everyday temperature, the conductor tension shall be 22% of the UTS. UTS means ultimate tensile strength. Above that point, the conductor breaks. So up to 350 spans on transmission lines, 22% of UTS. Okay, now if you get zebra conductor, the UTS is somewhere around 130 kilonewton, and you divide that by 4.5 or multiply that by everyday temperature, yeah, 4.5. Divide that by 4. UTS is divided by 4.5 or multiplied by 22% would give you the allowable everyday stress at the everyday temperature. So at everyday temperature, the conductor, sorry, I have made a mistake here. Now, at the maximum stress, that is the minimum temperature and maximum wind, the conductor UTS, the conductor stress should be 40%. That means at that temperature and maximum wind, UTS divided by 2.5 times or multiplied by 40% should be the working stress of the insulator. I'll talk about that again when we go on and on. You have to be maintain the ground clearance that is specified. Foundation has to be taken as good soil when you are calculating. Okay, if it's not good soil, then sometimes you have to do the soil testing for foundation designs. So to reduce the strength of the poles, the spans can be reduced. If you use 50-meter spans instead of 70-meter spans, the lighter poles with lighter breaking strength can be used. So this example can be explained by an example. I am coming to that we have a spreadsheet program for calculating and Newton reps and deriving of the tensions and all. So before that, I'll hand over to Vinavi to demonstrate PLS-CADD exercise for line design. Until she takes over and get the screen shared and all that, you can go on asking questions if you have any questions, and also you can have your snack and tea or whatever in between. Okay, Sashika, can you respond to Vinavi? She might be asking to share the screen.
Okay, sir. So you have to stop. So you have to stop the sharing.
Yeah. 1 second. Huh?
Okay.
I wonder whether you all have any questions up to that point. Okay, Veena. Sashika, is it all right to start this, or you need a little?
Okay, sir.
Sashika?
Yes. Shall we take a 5 minute?
Continue.
Shall we take a 5 minute break?
Okay, okay, fine.
Okay, thank you.
Fine.
Rienzie, sir? Rienzie, can you hear me?
Yeah, are you ready?
Yeah, ready, sir?
Yeah, shall we start?
Yes, we have a question, sir. Before,
अभी start करूँ मुझे?
sir, before go to the PLS-CADD session, there is some
Yeah.
questions.
Yeah.
First one is what
Yeah, මොකක්ද
sequence?
question?
Zero sequence impedance and the negative sequence impedance. Does they give those information from the data?
Can't hear.
Can you hear me, sir?
Can't hear. Chat එකේ දාන්න පුළුවන්ද? Question එක chat එකේ දාන්න බැරිද?
Okay, sir.
Hello. Hello.
Yes, sir. We can hear you.
Hello.
Hello, sir.
Sashika.
Yes, sir.
Hello.
Hello.
Sashika.
Yeah, we can hear you, sir.
Yeah. මොකක්ද දන්නේ question එක?
Sir, मैं chat එකේ දැම්මා.
All right. Yeah. නෑ මට හම්බුන්නේ නෑ බලන්න කියන්න.
Sir, මේක අහලා තියෙන්නේ positive sequence, negative sequence and zero sequence impedance of line. Does the data sheet give those information as well?
Positive sequence, negative sequence and zero sequence. Oh.
Impedance of
Hello.
a line.
Oh.
Does the data sheets gives those information as well?
No, no, not at all. Not at all. Now, you are given such data sheets in the software related data sheets, or you have to derive that with conductor properties given to a software like ETAP. So when you give the properties of conductor to ETAP ampacity program, you can get positives, negative, and zero sequence impedances from ETAP. And I'll show you some data sheets. I have shown ACCC data sheet already. I'll show you some more data sheets on the ACSR conductors. Hello, can you hear me?
Yes, sir.
So I think that question is answered.
Okay, sir. We can start the PLS-CADD session.
Okay.
Good evening, all of you. In this presentation, I will be explaining the process of modeling a transmission line using PLS-CADD software. This requires a series of steps to get a complete design done and will consume a little bit of time. So in this presentation, I will be explaining the important steps briefly to get a basic understanding of modeling a transmission line from PLS-CADD software. Hope everybody has heard about PLS-CADD.
Veena, may I interrupt? You are on presenter's view. If you can go to full screen, that might be better.
Sure. Now is it okay?
Not yet.
Now I'm in the full screen mode, so
Yeah, should be all right now.
okay. So PLS-CADD stands for Power Line Systems Computer Aided Design and Drafting. So it is a popular overhead power line design program on the market, and it runs under Microsoft Windows, and it has a graphical user interface. So the software includes the terrain, the structures and all the wires which requires to model a complete transmission line. So this model can be weaved in profile weave, plan weaves, 3D weaves as well. So basically, this is the process of designing a transmission line using PLS-CADD software. So I have divided the whole process into 7 steps, and I will go through each step in the further slides. So moving on to the first step, before you design a transmission line, first thing you have to do is to select the location, identify the starting and ending points of the transmission line. So for that, we are doing a walkover survey to identify the landmarks, road crossings, transmission or distribution line crossings, like that. So in this table, it indicates the data, the important data that you have to collect during the walkover survey for a successful completion of the design. So you have to collect the coordinates of the routes, the longitude, latitude, and altitude data, and building informations along the route and nearby the route, also the soil models, and if there are any trees along the route, that will be obstacles to the transmission line, and also more importantly, the land ownership details that you are going to acquire when you are doing the implementation of the transmission line. So in order to carry out a more accurate survey, like in the final design stage, you may have to use more accurate survey data to import to the PLS-CADD software. So total station is an electronic equipment which provide more accurate data. So it measures both vertical and horizontal angles, slope distance from the instrument to a particular point. And it also has an onboard computer to collect the survey data, and then you can import those data to the PLS-CADD software. But if you are in a preliminary design stage of a study, you can either use Google Earth Maps to locate the survey data. So you locate the survey data on Google Earth Maps, separately the line route data and the tower pole location data. So 2 KMZ files will be created, one for line route data and one for tower or pole location data. So here is one of the examples that we have worked out for a 220 kV transmission line design. You can see the line routes and the tower locations are marked on Google Earth Maps. So after you mark the locations and the route, you get 2 KMZ files. So what you have to do is, in order to import them into PLS-CADD software, you have to convert those KMZ files into an Excel file. It is important that you have to save the Excel files in CSV format. So for that, GPS Visualizer is one of the available online platforms that helps you to convert the KMZ file into a CSV file. As you can see in this Excel file, the acquired longitude and latitude data must be converted to XY coordinates system in order to import them into the PLS-CADD software. So depending on the location or the country, the coordinate reference system must be selected, and there are many online platforms available to convert the longitude and latitude data into XY coordinates. And the next important thing would be to enter the feature code data for each tower location. Depending on the location and the behavior of the line route path, you have to select the correct tower type. So you have to give each tower location what is the tower type that you are going to use in the design. So this is an example that I have extracted from CEB specifications, which gives the tower type with the feature code data. So whether, for an example, whether it is a suspension tower or a tension tower, if it is a tension tower, then what would be the angle? Or if it is a terminal tower, then the feature code differ from depending on the type of the tower. So after you convert the survey data into Excel form, then you have to enter this feature code data into the Excel file manually. Now, moving on to the next step, what we have to do is we have to create a structure data file. So from the structures tab, you can select create new structure, then you will get an interface like this. Here you have to enter all the data for each structure type that you are going to use in this design. So for an example, for each tower type that I have mentioned before, TD1, TD3, TDT, TDL, you have to create separate structure data editor files to each of the tower type. So this is an example done for a TD1 tower type. Then you have to enter the height of the tower and the description of the tower. And also you have to fill this table as well. So the set number means if there are two circuits in the transmission line design, the set number means the circuit number, and the next column gives the phase number, and the other columns, most of them give the specification of the insulator, the type of the insulator, what is it made of, and the weight of the insulator, the wind area, the length, like that. Attached trans offset means the distance from the midpoint of the structure to the insulator. And the attached distance below top means the distance from the topmost point of the structure to the insulator. So like that, for each tower type that you have created before, you have to create structure data file for the each tower type. And then one of the important things that you have to do is you have to go to this structure strength button, click the structure strength button, and then you will get a interface like this. There you have to define the allowable spans for that specific structure depending on the specifications. So this slide shows one of the CEB specifications for design spans. It gives the wind span and weight span depending on the voltage of the line for normal condition as well as broken wire condition. So depending on your structure type, you have to extract those data and fill this structure allowable spans interface from those data. Now the next step, now we have created the structure data files. Now the next step would be to create the criteria file. So there are a couple of criteria that you have to define. For an example, weather criteria, phase clearance, cable tension, like that. So you have to fill this data in order to simulate your design. So here's an example of a weather criteria interface. There you get to define the possible weather cases. So I have, in this example, here we have defined the hot plus wind case, everyday condition, cold condition, and ice condition. But in Sri Lanka, we don't usually simulate for the ice condition. So you have to enter for those three conditions, the air density factors, wind velocity factors, and the wind pressures will be calculated, and also the wire temperatures. So, and this is another criteria file that is created for structure loads. So in the description, you can see for tension towers and for suspension towers, both the normal and broken wire conditions to a specific weather case, you are defining some of the factors. So like the wire vertical load factor, wire and structure wind load factor, tension load factors, structure weight load factor, and structure wind area factor. So in most of the cases, these factors are defined in the specification. So you can directly enter this data to this structure file, to the criteria file. So the next important step is to select the suitable conductor for the transmission line. Here I have showing you an example done for a 1000 MVA capacity with N-1 contingency. The line voltage is 220 kV and with a double circuit configuration. So you can calculate the required line current per circuit, and it is 2624 amps. So the selected conductor is Amsterdam conductor, which is ACCC conductor, and which has a current rating of 1333 amps. So in order to cater the 2624 amps line current per circuit, we have to use twin conductors per phase. So like that, depending on your requirement, depending on your required capacity, you have to select the conductor appropriately. So then after you selecting your conductor, the next step is to create a cable data file. So following these steps, you will lead to a cable data interface like this. So this is quite easy. So if you know the exact conductor type that you're going to use in your design, you can directly import the data files from Powerline Systems website. Or if you could not find those data files, if you could not find your exact conductor in those data files, you can manually enter this data referring the manufacturer's catalogs. So like that, you have to enter the cable data into this cable interface. Up to now, we have created the CSV files, which contains the line route and tower locations, and the structure data files, the criteria files, and finally the cable data file. Now, the next step would be to model the transmission line in PLS-CADD. So for that, we are importing the CSV file that we have created before into this PLS-CADD software. So like this, you can import the CSV file to the software. Then you will get a profile view of the transmission line like this. So after you import the data file to PLS-CADD, next step is to add the tower structures to their appropriate locations. So on the locations where there is a structure, you have to add the structures like this. And as you specified before, you have to select the tower type from the previously created structure files. So like that, you have to add tower type to each of the tower locations from selecting the structure files that you have created. The tower types are in here. The tower types are TD1, TD3, TD6, TDL, and TDT. So after you locating, so for the complete transmission line, you have to select each tower with their correct type for each of the tower locations. After adding the structures, next step is to add the conductors. Here also you have to import the data for the cable type from the previously created cable data file and fill the other required data like the voltage, the conductors per phase, weather cases, like that. So for each of the section in between two towers, you have to add the phase conductor and earth conductor in the same way. So with that, we have completed the modeling process of the line. So this is an example that we have worked out for a 220 kV transmission line design. And this is a zoomed version of that. Here you can see the earth and phase conductors, the ground clearances, and the ground profile, and also the tower types. Now we have come to the final part of this exercise, the most important part, which is report generation. So there are a couple of reports that you can generate depending on the requirement. So as you can see in this slide, there are a couple of reports like the structure usage report, structure clearance report, summary report, and structure loads report, like that. So these reports are important when designing the structures or to get an idea about the loading conditions of the structures, whether they are in a satisfactory level or whether the towers are overloading and sagging of the conductors, like that. So here is a screenshot of a structure loads report. There you can observe the structure loads acting on each tower. So by that, you can design your structures to withstand that load and forces without structure getting damaged. So like that, you can generate the previously mentioned reports in order to design a complete transmission line system with a successful operation. So with that, we have come to the end of this presentation. Hope you enjoyed the session. Thank you.
Veena, it's not really the end of the presentation, so your part is over. Hello, Sashika.
Excuse me, sir.
Yes, we can hear.
Yeah.
So we have few questions with this regarding the session.
Yeah.
Sir, first question is, does data sheets give reactance or the inductance of a line?
Not at all, because now reactance, inductance are now okay. You are talking about the PLS-CADD software or the normal sheet that what I have shown you on ACCC conductors.
Yes, sir. Normal sheet.
Normal sheet now, it's only a conductor. Now, for your reactance and whatever, the capacitance or whatever, you have to finalize your configuration of the line. And with the configuration of the line, whether it's double circuit or single circuit, and with triangular formation or its vertical formation, all these factors would depend, the factors are dependents of your reactance. You understand? So you have to hang the conductors on a transmission line. After that only you can decide the reactance. You have done this in your theory, line parameters. Have you? Hello? Hello? Is it clear?
Yes, sir.
So, okay, after deciding now in PLS-CADD also, we have to give the configuration and distances and whatever the insulator types and insulator distances and creepages and whatnot to decide the reactance and okay, the positive sequence impedances and negative sequence impedances and all that. Even the software of something like ETAB would ask you the distances between the conductors and so on. So after that only it decides, okay, what are the reactances? Yeah. Sashika?
Okay, sir.
Thank you, sir. Sir, we have another question.
Yep.
So whether the demo or educational version of PLS-CADD is available? If so, could you please tell us how to get it?
I don't think so. Educational version of that software. Yeah, but I'll look for that. And we make a note that whether we can look for the educational version of PLS-CADD is available.
Sure.
To my mind, as far as I know, there's no PLS-CADD education version like other software like Power World and so on.
Okay, thank you, sir.
Yeah, shall we go on to the next session?
Yes,
Okay,
sir.
So I'm asking you to share the screen. Yeah, got it. Yeah, at this point, yeah, we'll go to the manual calculations. Okay, the software, the spreadsheet calculations of the equations what I have given in previous slides, especially one second here. This formula yeah, this one, and this formula. Okay, now yeah, we'll go to this spreadsheet. Now section. Now from you can see the spreadsheet, no, Sashika?
no, sir, we cannot.
You can, no?
No.
You can't?
No, sir, I think you have to share in, there's option. I think you have only share the presentations.
All right, yeah, okay. How do I do that? Tell me how to do.
So can you try this again?
Huh?
Can Can you try it again, the spreadsheet one?
Yeah. Can you see the presentation now?
Yes, I can see.
New share. I have asked for, right? And can you see now?
Yes, sir, we can see now.
Yeah. Okay. Now, say second column, S0 to S5. So S0 is the actual line in Trincomalee. So S5 is a tension tower. So 1 to 6 is one section. 2, 3, 4, 5 are suspension towers. Now from 6 to 17 is the next section. In between are all suspension. From 17 to 28 is one more section, and the last section is 28 to 33. Now the spans are given, okay, pole number, and then fourth column it gives the spans between each pole, right? S0 to S2 is 182. So next column you give the cumulative span length, and then which type of tower. TDT is the terminal tower, and TDS is the suspension tower, and TDM is a heavy suspension tower, and again S5 TDH is the tension tower. So angles are given in each tower point. Okay, up to about 10 degrees angle is okay. You can go as TDM has a 22 degree, so it's also a tension tower. The TDS on 5 is again a suspension tower, and TD5 tower number 6, pole number 6 is a tension tower. So we have taken this part as one section because this is too short, and we have derived altogether this one with this angle. Now sheet 3 gives you all the spans. Now first 3 spans, yeah, S1 to S3, yeah, from here to here, and that has been taken as taken as a section, and then sag at each span is calculated here. So at 75 degrees no wind, and sag at 175 degrees no wind, sag at each span minimum at 32 degrees, that is everyday temperature. Now here in this columns we have calculated the equivalent span first, and with the equivalent spans we are, after deriving the equivalent span, then we decide the tension at everyday temperature. So that is the UTS divided by 4.5 or 22%, multiplied by 22% comes to 6010, and sag at equivalent span here derived with the formula that is W L square over 8T. This is the weight in Newton, and this is the W4 is the equivalent span, and 8T. So after that, now in these columns, so maximum tension is here, and 15 degrees with wind is here, 75 degrees with wind is here, and 75 degrees with no wind is over here. Those are the sags. Sag at 175 degrees, that is the maximum sag of the conductor. Now here we have used Silvasa conductor, which is a ACCC conductor. That's why we have gone up to 175 degrees. Now in this sheet, 75 degrees with wind. So the equation what I have shown you for variation of the forces, wind forces or whatever, and then the variation of temperature is derived over here with Newton's Raphson. The line section 1, okay, the values are same. And these values for T2 are guess values until you converge that into a 0 over here. So you try on giving various values, okay, the values increasing little by little and all that. So it converges into a small value. And okay, theoretically, we have to get 0 over here to derive this, but it's not worth to do that because your 4th or 5th decimal is to be changed to get 0 over here. So 1250 T2, that is at 75 degrees with wind. So wind forces and the weight forces are calculated over here and applied over here, F1 and F2. The temperature differences are given over here, and for section 1 is this value, sorry. For line section 2 is 1187 and 1400, 1500. Line section 5 is 1590 and all that. So that is derived for 75 degrees with wind. So similarly, 15 degrees with wind, 75 degrees with wind, higher value. 15 degrees with wind is a lower value, and 75 degrees with no wind, further lower tension, and 175 degrees with no wind is the maximum sag and lowest tension. Okay, now going back to this one again. Okay, going back to 3, we have used the equivalent span value and the equation what we have learned in this thing to do the final calculation of the sag at 32 degrees. So 32 degrees equivalent span and actual span is calculated over here. So in each case, these are calculated here, and you have to make sure that your sag at 175 degrees would not violate the ground clearances what you have planned for and what is specified. So that is how you do the manual calculations of these transmission lines. So I'll send this sheet, not very user friendly, to Sashika, if you can share it. So you can play about it and see whether you can make it user friendly with whatever the data that is taken from various tables. So I'll go back to the presentation. Can you see it, Sashika?
Still, I'm not sure.
Can you see it now?
Okay, sir.
Yeah. So slides 28 to 36 explain the sample calculation, which I have now explained already. And we will see the spreadsheet program. Yeah, we have already seen the spreadsheet program. Now we'll skip all these calculations done manually. So this is the last equation what we have used in the spreadsheet, sag on equivalent span. So you do the sag, you calculate the sag on equivalent span for a certain condition, and then actual span length and equivalent span length square. So that is how you ultimately get the sag on any span. Okay, part 2. Selection of insulators. So I think this you can easily understand. The IEC 60071 gives you, table 1 gives you this recommended creepage distance. So now you know what is the creepage distance of an insulator. So light pollution level, number 1. Areas without industries with low density and agricultural areas, mountainous areas, and okay, Gol and Hammantota. It's not written here. You have a lot of trees and all. So anyway, agricultural areas, they have made a comment. Agricultural areas, if you spray the fertilizer, it can be cutting spray karna. The problem is it goes and deposits on the insulator. So if you spray the insulator or if you burn the wastes on the spots, then those places, agricultural places, are not taken as pollution, light pollution or pollution number 1. Anyway, when you have pollution, light pollution, they are recommending 16 millimeter per kV as the specific creepage distance. So to remind you, this creepage distance, first slides, that is your metal part, starting from your cap metal part, edge of the metal part, the surface a distance of the insulator from that point to the metal of the pin. The total distance is a creepage area. So the creepage distance for light pollution is 16 millimeter per kV, and medium pollution, that is areas with high density of houses and polluting smokes are very frequent, and you know, maybe some trains are passing with a lot of smoke, and sea, wind, and salinic pollution is possible. Those areas supposed to be medium pollution and 20 millimeter per kV. Creepage distance should be 20 millimeter per kV. Heavy pollution, that is areas with density of industry, lot of high density of industries, and lot of smoke and highways, this, that, and all. So then it comes to 25 millimeter per kV. Now, most of Sri Lankan lines has 25 millimeter per kV on their insulator strings. So, heavy pollution is areas extremely high pollution. You know, the contaminations on insulators are very high, and cement factories around, and desert areas where there is no rains and all that, that is very high pollution, 31. So in Middle East, they are using 31 millimeter per kV. Now this kV is the system highest voltage. Now, if you take 132 kV, you have to use 145. That is a system highest voltage, maximum voltage. So, if you take 25, if you use 25 as the heavy pollution, not very heavy pollution, 25 millimeter per kV, then you have to multiply 25 by 145 to decide the creepage distance of an insulator string of the transmission line. That is how you are calculating the now specific standard insulator, say we have selected heavy pollution and then required creepage is 25 millimeter per kV. Total creepage distance required 25 into 145, 3,625 millimeter. So each insulator, the creepage area is from this point, this is the metal cap, from this point along the surface and over the collars and up to this point. So that is the creepage distance. So say the creepage distance of this particular insulator is 302 millimeter. Number of insulators should be 3625 over 302. 12 numbers. Okay, this is actually a little higher side insulator with a little higher creepage. Now standard creepage of an insulator is somewhere around 254. So if you divide 3625 by 254, it would be somewhere around 14 or 15 insulators, right? So now if you are using, instead of 25, if you are using 20, then 20 into 145, right? That goes up to 2,900 something. Is that 20 into 145? Yeah, 2,900 odd, no? Okay, divided by 254, again comes to about 9 or 10 or 11 insulators. So if you go to the pollution level of medium, that is 20 millimeter per kV. Okay, that is how you select the insulator string, and if you calculate the same thing for the 220 kV, then 245 into 25, you get the value. You divide that by 302, then you end up with somewhere around 17 or 19 insulators. So in this slide, minimum impulse withstand voltage 132 to 20, 1050 to 20,050, and 132 800. So power frequency withstand voltage 300 and 395. Now power frequency withstand voltage is applied for 1 minute. 300 kV applied for 1 minute. So impulse withstand voltage, it's an impulse, it's microseconds. And for testing purpose, they are using sometimes very closer to a square wave or something of this order of kV. So minimum mechanical braking strength, that is the mechanical strength, 120 kilonewton. For 220, 120 or 100 kilonewton. Heavy suspension string set 120 or 160 for 220 and 132 kV 120. So these are taken from one of the CB specifications. Jumper suspension string set 70-70 and normal tension string 160. Light duty tension strings 70-70. So slack spans, there you can use 70 kN for the tension points. Otherwise, no. For longer spans, no, because the tension is high. So these are aluminium conductor steel reinforced data sheet. Code name: lynx, panther, lion, bear, goat, sheep, antelope, bison, deer, zebra, elk. All of these names are of animals, four-legged animals. And equivalent copper area, millimeter square. Sorry, these are here. Equivalent copper area, stranding and wire diameter, diameter over steel, overall diameter, aluminium area. So these are equivalent copper means if you are going to use same ampacity copper, you would have to use millimeter square 112 in aluminium area. Of this conductor is 183 actual. So amperage is given here, and DC resistance is given here, and AC resistance are given in various other data sheets, not directly on the manufacturer's data sheet. So ultimate tensile strength, this is important. Now, Zebra, you take 133 kilonewton, right? So 133 kilonewton over 2.5, 53.2, and for insulator. So we'll see now how these are getting connected in the next 2-3 slides. So insulator, actually you have to get 159 kilonewton according to the specified safety factors. So we'll see what are the safety factors. Now, conductors, earthwires and OPGW. OPGW is again, I'll remind you, this is the ground wire. GW is ground wire. It contains optic cables in a small tube inside the ground wire. So maximum working tension based on ultimate strength. So ultimate strength you have seen in this one. Ultimate strength of a conductor is always given in tables. So conductors, earthwires, tension based on ultimate strength. Safety factor is 2.5. Saying okay for 32 degrees, that is everyday temperature, the allowable tension is UTS, ultimate tensile strength, over 2.5. Now, sorry, this is the maximum. So maximum in the sense, okay, when is the maximum conductor stress is occurred? That is at the lowest temperature, sankochane vela, lowest temperature and maximum wind. At that condition, it's 2.5. So that is the maximum working tension supposed to face by the conductor. The conductor and earthwire at everyday temperature, at still air, then it's 4.5. Now what you do is you calculate the tension at everyday temperature and no wind. So you use the tension at 4.5, and under that condition, okay, you tension the conductor across the towers, and then at the maximum working tension, which is lowest temperature and maximum wind. So from region to region, from country to country, the minimum temperature and maximum wind differs. For us, we have, okay, we take for design purposes 140 kilometers per hour wind, which never has occurred in Sri Lanka. The maximum which has occurred in past history is 70 kilometers per hour, and the minimum temperature we are facing, maybe in not in Hambantota or Galle, but for designs in Hambantota or Galle, we are using 15 degrees temperature, 15 degrees centigrade temperature for designing the transmission lines. Yeah, for transmission lines in Nuvareli and other places, like very cold places, you are taking 0 degrees. And maximum wind condition to design the transmission line. So region to region and country to country, temperatures and the wind forces are different. Anchor clamps and mid-span joints. So the conductors are coming to port for a project in maximum 2 or 4 kilometer drums. Now what happens? For each 2 kilometer, if the drum is 2 kilometer, for each 2 kilometers, you have to have a mid-span joint. So the mid-span joint, ultimate strength, should be conductor or earth wire. Conductor or earth wire ultimate strengths into 0.95. So 95% of ultimate strength of whatever the conductor, the mid-span joint is used. So insulator strings and fittings at maximum working tension based on failing load. What does this mean? Now insulator string and fittings, we are going to find out what is the ultimate of a insulator string. So maximum working tension based on failing load, right? Now that is the thing we are trying to derive here. Now conductor maximum working load is this much. We have learned in few previous slides. Now you take zebra conductor 133 divided by 2.5, the maximum working load is 53.2. Now when this is 53.2, your insulator ultimate tensile strength should be 53.2 into 3, 159.6, that means 160. So you have to use 160 insulators in the tension points, definitely, because your maximum working load of the cerebral conductor is 53.2. So like that, next ones are okay, supports and foundations and whatnot. We are not talking about those things. And tower under broken wire loads and foundations under broken wire loads are important. Now, we presented, okay, she can derive the tower loading report on preliminary design that we are using to see whether our selected towers are okay on normal conditions and broken wire conditions. So this is a normal condition. Okay, the horizontal weight loads and vertical weight loads and horizontal the conductor tension loads and so on. This is a normal condition, and here you get a broken wire condition. We are checking always one broken wire conditions. So this shows 140.9. That means your conductor over here to this side is not broken. So it gives a tension of 140 kN, whereas the 106 kN has been there and that has failed. So minus that would make this 140 kN, and when you have that, both balance becomes 34.4 kN. Okay. Now, this is the normal condition and this is the broken wire condition. Like that, we are checking for broken wire conditions, and this is the load tree which we are using to design the towers and foundations, because those are the maximum loads that they are going to face. So for that loads, the design is performed. Okay, now slowly we have come to alien vibration. The bottom god or king Aeoli, right? Is making wind, and what happens? The conductor vibrates, horizontal vibrations and vertical vibrations, horizontal vibrations, and so on. And normal conditions, no wind, there are no vibrations. So this is a Stockbridge vibration damper with vibration of the conductor. It can swing to any direction because conductor cable joined over here. So this would amp the vibration damper, I think you got what I have told with the damper. It can move about and damp the conductor vibrations and would not transfer much vibration to the clamp here, the suspension clamp here. So closer look of the damper here, and you see a horse over here, right? That is called conductor galloping, right? Conductor galloping normally happens when Sashika goes out one day in Gaul or Hambantota. It starts snowing, and snow gets over deposited on the conductors, right? And what happens? Suddenly, after getting deposited, the sun rises, sun comes out, okay, the cloud goes out and is a sunny day. What happens? This snow gets melted and one portion would fall. When one portion would fall, what happens is the conductor gallops and then the whole thing goes on falling. It gallops more and more. It can damage the cross arms and towers and chop the cross arms. For such galloping is the snow deposited is very high, right? So it would never happen in Gaul or Hambantota. Don't worry, Sashika. So this one, of course, over here is a damage due to conductor vibration. Enough part 2 and transmission line maintenance. We are starting transmission line maintenance. So line maintenance, we are not going to much details on line maintenance. Cold line operations, work done under interruptions. Permit to work to be obtained to work under cold line operations. You switch off the line and do whatever you want on the line. Only thing, when the other line on the same structure is live, you have to maintain the clearances, and then you have to earth the conductors properly, otherwise there will be induced voltages and so on. So live line operations, that is called also hotline operations, work carried out with live line, interruptions not necessary. However, permit to work is necessary as auto recloses are blocked on line under hotline maintenance by system control. So permit to work is necessary. They should know that you are working on the line, hotline, and the interruptions are not necessary. When the conductors are live, the work is done. So line tools, this one is called a come along clamp, and whatever the cold line or hot line, the come along clamp is used to grip the conductor and tension the conductor to remove a conductor, to remove an insulator string and whatever. This is come along clamp. Hand winches are there. So with a hand winch on cold operations, you can tension a little a conductor with come along clamp and necessary wires, so that the insulator slacks a little, and you can remove the insulator and insulator string and replace it. Now, this is a large scale power winch, and you know, very big winches are available for various other work. Now, okay, what has happened? 1 second. Yeah, okay. Now, when you are conducting a line, say from one position of tension tower to other, you are stringing. So here you keep the tensioner, and on other side you keep the puller. So you pull it, and if something happens, now if the puller stops with the speed of the drum, you can't control it if the tensioner is not there. So tensioner stops the conductor drum rolling out if the puller suddenly stops. So this is the way generally they are doing tensioning. And let us see what these guys are doing. They are doing a hotline operation, and a come along clamp is over here, and with a hot link stick, they are trying to tension the conductor little. When this one is little slacked, they are handling the insulator string to be removed from the cross arm, and then they can replace another one. They can do all the complete operation with these sticks. These are 33 kV line with 3 insulators. So some other tools. This tool is called gripple stick, and there are many tools that can be connected to gripple. And hotline maintenance tools, some of the maintenance tools. There are many maintenance to hundreds. These are link stick, strain stick. And the next one is, this one is strain pole. This is the insulated section, and this is the clamp that can be strained. There is a big interruption, no? Okay, this is called an insulator cradle, and yeah, this come along clamp can be connected over here. So this one is called, this one connected, the come along clamp is connected over here, right? This yoke is called front yoke, and this is called the back yoke, right? And with the sticks, you can put the come along clamp to the conductor, and this one connected to this, and this part over the end of the insulator, where the maintenance men are there now, right? So they can put the chain or fix the chain onto the structure of the transmission line, and then by turning these, they can strain they can tension the conductor over the something like this. Now it's not very so what you do is you put the strain poles over here. This man is doing some bare hand operations. I'll tell you what is a bare hand operations. He is at the dangerous end, that is at the 400 kV of this should be a 400 kV. 400 kV in doing some operations at that live end. I'll tell you how to do that. This is a insulated ladder, and all these parts are insulated. So the strain poles and yokes are put to the conductor and stressed, and when the insulated string is little slacked, they can remove it and put a new one that is over here. So what these people are doing, okay, they are putting a insulator onto this conductor and they are trying to raise it. These are two strain poles, okay, with the insulator cradle. They are going to raise it up to here and connect it. And here also a suspension point. This is a back yoke over here on the cross arm, and they have put two poles. This is the front yoke. So with the front yoke, these two conductors are gripped, and he is going to lift the conductors a little up. While lifting the conductor with strain poles, with link stick or strain poles, they can also support this conductor to stay away from the people over here. So when the person here can remove the connection over here, the locking device, and then take it out of the clevis over here at the suspension clamp. So this is the top yoke here, top cross arm yoke. So what are these guys doing? Okay, they are also removing the conductor by stick operation and holding the conductor over here, and this insulator is already removed. This side is removed, and with hot sticks, and they are lifting the conductor a little to get a little slack on the insulated string with these two strain poles over here. What are these guys doing? Now, these guys are going to remove this total cross arm with insulators. Conductor covers over here, that can be put using the grip ball. Sticks, and then this arrangement, what they have done is remove the binding on the insulators over here, the connections, and then they are going to lift this portion so that the conductors are lifted over the cross arm. After that, when they lift this enough to have safe clearance, then they can remove the cross arm with the bolt here and replace a new one. So this is the bare hand operation. One moment again. Yeah, bare hand operation. This man is sitting at the live conductor, and this is the guard ring. Right, and he is wearing a kit, this kit. What is that kit called? The bare hand kit. So it covers your head and the arms, and shoes are components of bare hand kit. And all these are, guess whether this is insulated or conductive kit. It's a conductive kit, right? You go and get over here, and this kit has a clip. That clip can be connected to the conductor. Then your potential comes up to 400 kV or 220 kV or whatever. So this man, I suppose, is more than 400 kV due to the number of insulators. It may be sometimes 780 kV insulators. So bare hand operations, of course, is easy for higher voltages than 400 kV, because your sticks cannot be handled at such a distance, and it's very difficult to keep the safety clearances. So bare hand operations are better. So now this man is not doing bare hand operations, he's at the dead end, that means the tower end. This man is doing the bare hand operations, he is touching the 780 kV. So when you go with this kit and hook onto the conductor at that potential, you hear the sound of 100 frequency. I mean the 100 frequency. So the connections of come along clamps, this, that, and whatever the yokes, and all can be done by this man at this end, and it's easy way to remove the insulator. And this is actually conductive in the sense that this is a semiconductor. Semiconductor, okay, now right at the last insulator, it's 780 kV, we'll say 220 kV. And after one insulator, if you accidentally touch, is a different voltage, and maybe some 20 kV, right? So if you touch that, your current through the kit would not be so much. So that's why it's semiconductor, and even shoes are semiconductor with yeah. So while you are here, you keep energized at the voltage of the conductor. So that's all, and I want to share the screen for something else. New share, and no, I can't share that because can you see this? Can you see this,
No, sir.
Sashika?
No, sir.
You know,
No, sir.
Nadda.
Yes, sir.
Put in the new share. බෑ සශක එක අමාරු මට වීඩියෝ එකක් පෙන්වන්න ඕන චුටි anyway දැන් පේනවා ඇති
Okay, sir.
සශක
Yes.
දැන් පේනවද
Oh, sir. Pen.
මේ වීඩියෝ එකේ තියෙන්නේ ඇත්තටම ඔය නෝරොච්චෝලේ නිව්චිලාව අතර 220 kV ලයින් එක ඒකේ ඔය සැලිනික් පොලියුෂන් නිසා වෙන partial discharges ඔකට කියන්නේ දැන් ඕකේ salt deposit එක කියන්නේ salt වතුර එකත් එක්ක ඇවිදින් deposit වෙන නිසා partial discharge. So partial discharges වෙලා ඊළඟට වෙන්නේ අදිත්‍යම flash off. Now flashovers are very common in Putlam area because of heavy pollution. Over partial discharges. Some are saying this is corona. It's not corona. It's partial discharges. Corona is always. Can you hear me, Sashika?
Yes, sir, we can hear.
Now we are coming to an end. Now at the last video, we have seen partial discharges. Corona is, of course, now when you go towards, say, Norelia, if you go in very high fog and all, then you see sometimes transmission line near insulators, some glowing blue light like. So that is corona. The corona is always okay, as dangerous as the partial discharges, and ultimately it can flash. Now, to our advantage in our country, every month there is even a small drain. So I used to say, okay, our insulators are washed by God. So we are lucky. Now, in Middle East and all, when the rain fails and fog comes and, sandstorm comes and all that, the insulator flashovers are very high. Even they have gone for 31 millimeter per kV for their insulator string crimpage distances. So we are going to have a little time for questions and answers if you are interested. So that is the end of the maintenance work. And anybody wants can ask your questions. No questions, Shashika? Hello?
Hello, sir.
Questions now again, eh?
Hello, can I ask you a question?
Yep.
So I'm Charit, and my question is regarding vibration dampers.
Yeah.
So I have seen in India, there are two sets of dampers in one conductor. in some transmission lines, it has only one vibration damper, and in some transmission lines, there are two dampers. In the design stage,
Yeah.
how do we decide whether to put one damper or two dampers? Is there any calculation behind that?
Yeah, and there are okay, now I'll start with this. Now the transmission line profile design is actually belongs to mechanical engineers, but they never do that because they don't know how this is done, and electrical engineers are learning this, and we have encroached into that mechanical part, right? And this is basically the properties of material. And now the Stockbridge damper is also, there are various, the lens and the two side cap weights are differed, and whatever, that has properties. So with that properties, there is a calculation of how many dampers needed for such and such span. And yeah, there is a calculation. So that calculation is also very, connected to vibrations and mechanical engineering.
Thank you, sir.
Sir, we have another question.
Yeah.
What will be the lifetime degrading approximately with the partial discharge in Orochola area, sir?
You are asking what is the
approximately lifetime degrading.
Time degrade of an insulator because of partial discharges.
Yes, sir.
Yeah.
Yes, sir.
Is a difficult. Is the most difficult question I have ever faced, but I know the answer. Now, after flashing over once or twice, the insulator is, no more left at the transmission line, because it's again and again may flash over. Because of that, it's changed. So every year there's an inspection, and when there is a flashover and heavy partial discharges, it leaves white marks of these discharges on brown porcelain insulator. It leaves white marks. So when they see the white marks, they change the insulator. But there is a solution for that. That solution is applying Dow Corning 370. That's a silicon rubber paint. So Dow Corning 370 paint is applied on the insulators, would stop such partial discharges. So then you can use that for maybe so many years, like 20 years or 25 years, until your pin get corrodes and, I think I have answered the question.
Yes, sir. Here we are highly encouraging you to ask the questions. If you have any question regarding today's session, feel free to ask from Mr. Rienzie directly, or you can leave your question in the chat feature.
Yeah, of course.
Hello, sir.
Yeah.
I'm Kason. So my question is when we when we implement the transmission line, after its implement, with the time there will be elongation. So uh, so if it happen, there will be the disturb the clearance. So uh, when design the transmission line, how it can take into account. That means there will be, we have to consider the creep compensation.
It was not clear, Hashan, because it was breaking a little. Can you repeat the question if it's possible?
Hello, sir, can you hear me?
Can you please repeat the question? Yeah,
When
now it's okay.
yeah, uh, when we implement our transmission line, with the time it will, because of the weight, it will be elongate.
No, Hashan, it's breaking. It's breaking. It's breaking. No, Hashan, it's breaking. Can't hear. Anybody got the question clearly? Can you type it?
Sir, he's asking after implementation of a transmission line, it gets some elongation. So with the time, with this due to the expansion and all those things, so it will disturb the clearances. We get the design stage. So he asking how can we
Right. Okay. That is called conductor creep. Yeah, Winra. Now that is called conductor creep. Can you hear me?
Yes, I can hear you.
Yeah. Now that is called conductor creep. So at the design stage, you leave about 300 millimeter for the seg. So sag is so much. You allow another 300 millimeter for the sag, so that with the conductor creep, after maybe 10 years, the creep okay stops and is no longer creeps, but the ground clearance is maintained. So it's a matter of about 1 foot.
Yeah. Okay. Thank you.
I think I have answered your question.
Yeah. Hofsters, I think the
Hello.
yes, I think Kasun is clear about it.
Hello.
Yes, sir, we can hear you.
Yeah. Any more?
Hello, sir. I'm Ramal.
Yeah,
My
Raman.
question is, when considering this, the GPS distance, as you mentioned, it depends on the pollution level, right? So, in Sri Lanka,
Yeah.
my question is, when the transmission line, which is close to the sea area, is it still enough to use 25 millimeter for kilovolt GPS distance? Because in the sea
Yeah.
area, we have the salt
Yeah.
free
Yeah.
Polisher.
Yeah. Ramal, you may have seen when you are coming from Galle to Colombo on the not on the highway, on the normal sea way, there are some insulators with white paint. That is this Dow Corning paint, right? So to my mind, of course, when it's sea area, when you have sea pollution and also near the cement factory and all, even 31 millimeter per kV is not enough. So solution is keep 25 millimeter per kV, and when you have problems, if you have problems with sea breeze and whatever, then if you have repeated problems, go for Dow Corning application. Apply Dow Corning paint and forget it. So it won't flash over. Clear?
Please, sir. Thank you, sir.
Any other questions? So, Sashika and guys, ladies and gentlemen, and
Sir, excuse me, sir. So one of
On
our
a-
participants have asked the question. One question. What is the use of Smith charts
Yeah.
in transmission line?
tell me that again.
What is the use of Smith charts in transmission lines?
I didn't get it. What charging?
Smith size of the Smith charts in transmission line. Can you hear me, sir?
Still, I didn't get the question.
Sir, what is the use of Smith charts in transmission line?
Smith charge.
Yes, sir. Smith charts.
I've never heard of that. Sorry. Smith chart.
Yes, sir. One of our participants is asked that.
No, I have not gone through that.
So I think it's not it's
Smith chart.
related with the electrical. I think it's related with the telecommunication. I think, if I'm right.
Maybe. I've not gone through that. All right. Okay. Are there any specific way to earthing tower line? Required value for earthing? Yeah. Now, required value of earthing is always taken as 10 ohms, and it's always measured with high frequency earth tester, and that is supposed to be the surge impedance of the earth. Now, for a surge, when it's discharging, say 10 kiloamps is discharging, 10 ohms, right? And then you get about 100 kV, 10 ohms, and 10 kA, so 100 kV potential uprise at the tower foot, right? If that is more, it would backflash. So required amount is the 10 ohms surge impedance. Otherwise, it would backflash, and in the event of surges, it would backflash. So the way of earthing is, you say it's counterpoise earth. It's just a conductor. Okay, we'll say 75 millimeters square or 120 millimeters square conductor joining the four tower legs, and then taken out to a certain distance and earth with a rod. But that is not a very safe way, because when it's discharging, what happens is there will be potential differences, step voltages and touch voltages around the tower. So if you know anybody who is working around the tower, number one is, if suddenly it gets okay, raining and lightning, what you should do is you should take very short steps to go out of the place from the tower. And working with memories and long tools or whatever is forbidden. You should not do that, because it's not a very safe way of earthing around the towers. I think that question is answered. In previous video, I have shown continuous partial discharge. This is not a transmission system. What kind of? Yeah, the solution is okay. Again, the Dow Corning 370 apply, and you'll get rid of all this sort of. Now, Dow Corning, when it's applied on the insulator, the contamination never collects as a uniform film, because like you know, the paint itself forms certain microscopic bucket-like things, so that the dust get collected on that buckets and washed away with wind and rain, because it's very, very, very hydrophobic. It doesn't stick onto the paint. Now, what happens on the insulator is, if it's not washed properly, the film of contamination would remain for a long time, and you know, the partial discharges occur through surface flashover. Okay, surface parts. Okay, any other questions? Hello, Swastika.
Yes, there is no any
Uh,
questions.
so it seems there are no other questions. Uh, so in order to end up the today's session, I would like to thank Engineer Rienzie Fernando and Ms. Veenavi Vasundara for delivering a valuable session. I hope that everyone has added good amount of knowledge and shaped up their ideas from today's session. Again, thank you for the guest speakers for allocating your valuable time for us in this holiday. Thank you everyone for joining today.
And thanks for the opportunity. It's very nice to talk to you guys. Young, fresh minds of the future, and share my knowledge, whatever I can. And yeah, thank you very much.
Yes, sir,
And
it was
good
a
night.
pleasure. Thank you. Good night, sir. Good night, everyone.